Hello everyone, welcome to our channel Mathematics Pathshala. This is some questions of memory based question of CSIR December 2023. So there are some problems from linear algebra which are completely memory based. So now we try to solve these questions. First see, this is the first question. They are given that the given blocks of matrix A 7 by 7 are this. So A is a matrix which is a matrix of order 7, matrix of order 7, and this is the blocks for the matrix A. Now which one will be true? First option says that characteristic polynomial is this. So see here first. Clearly this is the blocks of the matrix A. So it is clear that the eigenvalues are 0, 1 and 2 pi I, and corresponding to these eigenvalues, these are the blocks. So 0 appears here in this block one time, in the first block. In the first block 0 appears one time, so this is a Jordan block for 0 of size 1. Then it is Jordan block corresponding to lambda equal to 1 of size 1. This is Jordan block of 0 correspond of size 2, because this Jordan block there are eigenvalues in diagonal position and 1 in super diagonal and all other positions at 0. And now this is 2 pi I 1 0 0 2 pi I 0 0 0 2 pi I. So clearly this is not a Jordan block for 2 pi I of size 3, because if it is a Jordan block for 2 pi I of size 3, then this super diagonal position should be 1, but it is 0. So this is like, actually there are two blocks. This is one block for 2 pi I, this is one block of size 2, and this is one block for 2 pi I of size 1. So now this is clear that how many blocks are there of which size. And now see, 0 appears here 1 for this block one time, and for this two blocks. So there are algebraic multiplicity of 0 is actually the sum of sides of this block. So this is 3. So x cube is a factor of this characteristic polynomial of this matrix. Then 1 appears exactly one time, so x minus 1, 1 algebraic multiplicity of 1 is 1, and 2 pi I appears for this two size block 2, and for this one size block one time, so 3. So algebraic multiplicity of 2 pi I for this matrix is 3. So x minus 2 pi I whole to the power 3 is a factor of this characteristic polynomial. So this is the characteristic polynomial. We can denote it by chi ax. So this is the characteristic polynomial of A. So option 1 is the correct option. Now see minimal polynomial. So minimal polynomial, we know that uh, the uh, the size of the largest block corresponding to a particular eigenvalue, say lambda, is equal to the number of roots appears in minimal polynomial. So here for 0 the size of the largest block is 2. This is the largest block corresponding to 0, so is 2. So x minus 2, sorry, so for 0, 0 will appear two times in minimal polynomial. So x minus 0 square, that is x square, will be a factor of minimal polynomial. And then for 1 is appears one times, this algebraic multiplicity 1, and also so largest block size 1, so x minus 1 will appear one time. And for this 2 pi I, there are two blocks corresponding to 2 pi I, and the size of the largest block is 2 for this 2 pi I. So x minus 2 pi I square will be a factor of minimal polynomial. So this is max should be the minimal polynomial for a. So option 2 is also correct option. Now see, eigenspace for eigenvalues 0, 1, 2 pi I are 2, 1, 3 respectively. So see here, there should be dimension of the eigenspace, because if there is not written dimension, though then it will not be a valid statement. So there must be dimension of the eigenspaces for eigenvalues 0, 1, 2 pi I are this respectively. So now see, for this 0, we also know the number of blocks, the number of Jordan blocks corresponding to a particular eigenvalue is equal to the geometric multiplicity of that eigenvalue, and geometric multiplicity is equal to the eigenspace, dimension of that, the eigenspace of that eigenvalue. So geometric multiplicity of 0 for this matrix A is equal to actually uh, is equal to our dimension of the eigenspace E0, that is denoted by, so this is actually null space of A minus lambda I, that is null space of A minus 0 I, that is A. So this is actually, we denote this by eta A minus 0 I, that is eta A here. So see here, for 0, there are two Jordan blocks, one of size 1 and the other is of size 2. So there is two Jordan block. So geometric multiplicity of 0 equal to 2, and that is the eigenspace of the eigenvalue 0. And then geometric multiplicity of 1, that must be 1, because algebraic multiplicity of 1 is 1. Then geometric multiplicity of 2 pi I. See here, for 2 pi I there are also two blocks. There are also two blocks, so it will be also 2. So the dimension of the eigenspace for the eigenvalue 0 is 2. For 1 it is 1. For 2 pi I it is 2. So option D will be the correct option. And option C, there is written that the dimension of the eigenspace for the eigenvalue 2 pi I is 3, which is not correct. So it is not the correct option. So option A, B, D are the correct options. So this is the solution for the question 1. Then we come to the question 2 and try to solve this. See the question first. There is given that two matrices X and Y are two n by n matrices such that these conditions hold. Then which one will be true? So for this expression, this is very easy to see that xy minus x square minus x equal to I, and so x into y minus x minus I equal to I. So x into something, another matrix equal to I, which implies that x is invertible. So clearly option 1 is the correct option. Now see, y is invertible. Actually it may not be true, because if we take y equal to 0 and if we take x equal to, just you verify, this is a very easy exercise for you, that if we take a matrix this for n equal to 2 here, 2 by 2 matrix. So then this is very easy to see that this matrix will satisfy, actually the characteristic polynomial will be lambda square plus lambda plus 1 here for this matrix X. So X will satisfy this equation, x square plus x plus I equal to 0, and then since y equal to 0, this expression will be true. And since here y equal to 0, so y is not invertible. So for this option B is not true in general. Now see, if we take, okay, first let us option 3 we will check. See here, xy equal to x square plus x plus I. So from here we have y equal to, because x is invertible, x inverse exists, so we can take matrix multiplication by x inverse. So we have x plus I plus x inverse. Then just we again multiply x, uh, post multiply by x, matrix multiplication, and we get x square plus x plus I. So see, xy equal to this and yx equal to this, so xy equal to yx. This is very easy to prove. So option 3 is the correct option. Now see, I plus x is invertible. Here we can take x equal to just this matrix, just minus 1, minus 1, minus 1, and all other elements are 0. So this is actually minus I. And we can take y equal to I. Then see if this expression satisfied or not. So here xy will be our minus I into minus I minus I square. So minus I square. So it will be actually I. And for the right expression, x square plus x plus I, it will be x square will be I, x will be minus I plus I, so it will be also I. So see, xy equal to x square plus x plus I satisfied, but x equal to minus I. So clearly x plus I or I plus x will be null matrix, so it is not invertible. So option 4 is not the correct option. So option A and option C are the correct options, and B and D are not the correct options. So this is the solution of this question. Now we come to the question 3. See, this question is a very interesting question. A is a 3 by 3 matrix, and the elements of A are in this way defined, that for the first row this is 1 1 position, so it is 1 into 1 1. For this position 1 2, that is 1 into 2, that is 2. 1 3 position, this is 1 into 3 3, and like this is 1 into n n. For the second row, this is I equal to 2 and j varies, so 2 into 1 2, this is 3 into 2 into 2 4, this is 2 into 3 6, and so on. This is will be 2n, and the nth row will be n 2n up to n square. Now see, this is the matrix A, and it's very easy to see that here date A will be 0. How? Because if we take date A, just take 2 common from the second row, then the first row and second row will be identical, so it will be 0. So since data equal to 0 and it is also the product of the eigenvalues of A, so 0 must be one eigenvalue of this matrix A. So we have 0 must be one eigenvalue for A. Now, and also the sum of the eigenvalue, we know that if lambda 1 lambda 2 lambda n are the eigenvalues of, then this sum will be equal to trace A. So this will be 1 plus 2 plus up to n square, and we also know 1 plus 4 plus, actually this is 1 square, we can write 1 square plus 2 square up to n square, and this sum we know n into n plus 1 into 2n plus 1 by 6. Fine. Now see, we will consider the algebraic multiplicity of 0, and for this first we consider the geometric multiplicity of 0, and for this first we check what is the rank of A here. what is the rank of A? Now see, just write the matrix A. This is 1, 2 up to n. This is 2, 4 up to 2n and so on. This is n to n up to n square. Now, if we apply row to find the row reduced form of A, if we apply row operation, then we will write this R2 plus minus 2 R1. Then our second row will be 0, 0. All element will be 0. First row remains unchanged. 1, 2 up to n. We apply the operation on third row by R3 plus minus 3 R1. Then see it will be just 0, 0, 0, and similarly we apply for all row Ri plus minus I R1. So for nth row it will be Rn plus minus n R1 and it will be also 0, 0, 0. So see, it is the row reduced form for A, and so there is only one non-zero row for A. So rank of A will be here 1. Rank of A will be 1, and by rank nullity theorem we have nullity of A plus rank of A will be the number of column of A, that is n. So from here nullity of A equal to n minus 1. So also nullity of A means our nullity of A minus 0 that is our dimension of the eigenspace corresponding to the eigenvalue 0. So this is equal to n minus 1, and this is also equal to this is actually geometric multiplicity. This is the definition of geometric multiplicity of an eigenvalue. So this is geometric multiplicity of 0 for A. This is n minus 1. So since geometric multiplicity of 0 is n minus 1, so algebraic multiplicity of 0 must be at least n minus 1, since A is a n by n matrix. So it may be n minus 1 or n. So if it is n, then all the eigenvalues will be 0. So this sum cannot be a non-zero value. So one eigenvalue must be non-zero. So it will be n minus 1 exactly. So algebraic multiplicity of 0 is n minus 1 and another eigenvalue will be non-zero. So there are n minus 1 terms will be 0 and one term must be equal to this. So there are two eigenvalues. One eigenvalue is 0 of multiplicity n minus 1 and another eigenvalue is this, the sum element, that is n into n plus 1 into 2n plus 1 by 6 of multiplicity 1. So our characteristic polynomial for A will be lambda to the power n minus 1 into lambda minus this element n into n plus 1 into 2n plus 1 by 6. So this will be precisely the characteristic polynomial of A. Now look at the options. It says that one of the eigenvalues A1, so it is not the correct option. One of the eigenvalues n, it is not the correct option. One of the eigenvalues this, it is not the correct option. One of the eigenvalues is this, is the correct option, because we have two eigenvalues. One eigenvalue is 0 and other is this n into n plus 1 into n plus 1 by 6, and also the multiplicity is calculated now here. The algebraic multiplicity of 0 is n minus 1 and the algebraic multiplicity of this eigenvalue is 1. So this is the solution of this question. Option D is the only the correct option. Here written some with mistake. This will be D. This will be option D. Okay. So this the solution of this question, and so we have discussed three questions from linear algebra and for the exam CSIR December 2023. Okay. Thanks for watching.